Hi, and thank you so much for having me. It's a real honour to be asked to do this keynote. It's been a rough year, I think we can say, and this is my most positive talk. This is a look at where we are, how far we've come in the last 30 years, and where I think we're going in the next 30 years, and the things that we should be thinking about and getting excited about. And I've called it Futurology for Developers. And I'm just going to share my screen here. And I was giving this talk last year because last year was the 30th anniversary of my first job in tech. And I looked back over those 30 years and where things were when I started, and then thought about what we could guess about the next 30 years based on that. So yes, but no, I have been working in tech now for 31 years. And when I first started back in 1989, this was the server that I worked on with 7 other programmers. And we had Wyse terminals connected to this using serial RS-232 cables. And this was a 286, and it had 2 megabytes of RAM, which was maxed out. And it had a 150 megabyte hard disk. And we would work on this, and we would spend the morning until about 1:30, 2 o'clock in the afternoon writing C code. And then we would start the build. And then we would go and play table tennis for 2 hours while we waited for the build to complete. And I'm not making that up, we actually did. And if you broke the build, you were the one who had to stay late and fix things so that it worked the next day. And if nobody broke the build, then whoever came last in the table tennis tournament had to stay and do the setup and make sure that everything was ready for the next day. So this thing had an Intel 8286 processor, and it ran at 8 megahertz, not gigahertz, megahertz. It was single core. It had 134,000 transistors, and it didn't even have floating point operations per second because it didn't have a floating point operator. You could buy an Intel 8287 coprocessor if you needed floating point. And this was the state of the art. And actually, you know, business being what business is, the administrative and sales side of the operation had a 386. The programmers had a 286. Go figure. But yes, and then Moore's law obviously kicked in. Moore's law says the number of transistors in a dense integrated circuit doubles about every 2 years. And this has held true one way or another since the 1960s. And it's still holding true today, although we are coming up to the limits of it. So yesterday, for example, Apple announced their new Apple Silicon for the Mac range, and the first chip in that is the Apple M1, and that runs at 3 gigahertz, 375 times faster than the 286. It's got 32 cores of different kinds. It's got 16 billion transistors, and on this picture here, the 16 billion transistors are in the sort of brightly colored square, the 2 chips off to the side, onboard memory. But the 16 billion transistors are just in that little chunk of silicon. They're 5 nanometer transistors. It's a 64-bit. It doesn't even care about MIPS. And teraflops, it's like 2.4 teraflops for the CPU and GPU. But then it's got a neural processing unit that does 10 billion neural operations per second. It's just insane. And that's basically a mobile chip that's been pulled out to be put into laptops and desktops. In the desktop side of things, we have things like the AMD Ryzen Threadripper, which is a 64-core processor with 128 threads that has 15 billion transistors, and we're expecting the 5000 series Threadrippers to be announced by AMD soon. So processing power has just gone insane. And I just want to give you an idea of what the 1.5 micrometers versus 5 nanometers actually looks like. If I shrink down this 1.5 micrometer transistor to a 5 nanometer transistor, it basically goes like this. So that was a big picture of a transistor, and over on the other side there is actually, I carefully worked this out, there is a single pixel which represents the smaller transistor. It's just there. And that's what's happened in the silicon space. That 286 had 2 megabytes of RAM on a SIM, and this thing cost thousands of pounds at the time. This was really expensive. Now, for a couple of £100, couple of €100, you can get a 32 gigabyte SO-DIMM to put in your laptop, and that's 120 times faster than the old RAM. So memory's got faster. This was the disk. This was a full height 5¼ inch SCSI hard drive, 150 megabytes. Just to give you an idea of the scale of this thing, here it is next to a London bus. Okay, it wasn't quite that big, but it was big. Now Samsung are now selling a 4 terabyte micro SD card, and if I shrink that down so it's the correct size, that is about the size of one of the screws in that 150 megabyte hard disk. So storage, and the 4 terabyte card is probably about the same price. Again, we're talking thousands of euros for 150 megabytes of storage back in those days. We worked on these things, Wyse 50, black and white, or green, black and green, or black and orange, depending on which one you had. Had no processing power at all. It was just running against a Unix machine. You could actually buy laptops back in those days. This was the compact portable 286, and this thing cost £6,000, weighed 6.4 kilos, had 640k of RAM and a 40 megabyte hard disk, and would last for about 3 hours on battery, and that was £6,000. Now you can get a Lenovo ThinkPad X1 Extreme for £2,500 that's got more processing power in it than probably existed in the whole of the United Kingdom in 1989. We had a printer, we had a dot matrix printer, and for code reviews, we would use this thing to print out code, and then we would get round a conference table and mark it up with highlighter pens. That was how you did code reviews in 1989. And so printing out the code, it made a noise like this. The older people in the room will remember that noise, and the younger people in the room are just going, what? Why would a printer make a noise? It's because it had pins, and the pins were just hammering on the paper through a typewriter ribbon. And of course, back in 1989, we just didn't have certain things. There was no internet. I learned C from a book. I learned the frameworks and things that we were using from ring-bound manuals. If I didn't know how to do something and nobody else in the office knew how to do something, that was it, basically. You got on the phone and waited in a queue to talk to somebody who knew something more about it. There was no internet at all. We did have networking, admittedly, but we didn't have Wi-Fi. So networking was cables, and we had cables, twisted pair cables, where at the end of the network, you would have to put a terminator onto the last connector in the network cable. And if you didn't put the terminator on, then it would just stop the entire network from working. And if you wanted to add another computer, you had to take the terminator off and then add another chunk and then put the terminator on at the end of the next one. There was no such thing as the cloud. And so if you needed a new server, you had to fill out a form, and then somebody would ship you a server, and then you drag it into the server room, and that would take 6 to 9 months. Whereas now we can just go, oh, I need a new server. I need a new Kubernetes cluster. I need a new high performance artificial intelligence GPU tensor core accelerated cluster to run a 5 petabyte data set, and I've only got an hour. I'll just spin up 1,600 massive servers and run the thing against all of those all at once. We didn't have devices. We didn't have any, there was no mobile device. There was nothing you could carry around in your pocket. I've got more computing power in my pocket than existed in the world in 1970. And I'm guessing you guys have too. The first portable thing was the Apple Message Pad. I don't know if anybody ever had one of these. I got to play with one back in the day, and it was terrible. It was one of the worst things Apple ever made. It couldn't keep up with the pen. It was a seriously low resolution, no backlight, and this thing weighed 640 grams. That's more than a pound. It was a brick. Now, of course, we've got things like the Apple iPhone XS, which came out in 2018. We've got the iPhone 12, which has just been released, which is just ridiculous. And these things weigh about 177 grams. So we've made a lot of progress over the last 30 years. Things have got faster, things have got smaller, things have got lighter, things have got preciser. Manufacturing and making chips, the reason we can do 5 nanometer now is because we have extreme ultraviolet lithography processes. Things have got powerfuler. I am making up words now. But yes, everything is much more powerful than it used to be. Things are connected. Everything is connected to everything else. And so my new hobby is extrapolation. It's to take the rate of progress that we've seen over the last 30 years and bear in mind that progress is accelerating and continues to accelerate, and just guessing what that might be over the next 10 or 20 or 30 years. So if we extrapolate Moore's law out to 2049, for example, then we would have chips with 328 trillion transistors on them, which isn't actually likely to happen because we're hitting up against the point where the transistors are basically the size of a silicon atom, or certainly not very far off. Quantum chaos is starting to cause problems, and you can't make chips bigger because every transistor on the chip needs to be within a clock cycle of every other transistor on the chip, and you start running into the speed of light. You can't, the reason chips, they don't just make chip dies bigger is because an electron can't get from one side of the chip to the other side of the chip in a single clock cycle because it can only travel at the speed of light. So Moore's law is going to stop at some point very soon. And we are not going to see 328 transistors. We're seeing 5 nanometer is available now. We're seeing 3 nanometer is apparently going to be available. There's talk of 1.4 nanometer using different materials and maybe switching away from silicon to something like graphene. But this is an electron microscope view of what the inside of a processor looks like at the moment. These are the transistors bumping up against each other. We cannot make them much smaller because we will be literally putting atoms together if we start doing that. So there are possibilities for what we can do with processors. I said different materials. So silicon germanium is what's currently being used to achieve 5 nanometer and 3 nanometer and so forth. There's talk and research into making processors of graphene and carbon nanotubes. If they can get that working, that will be awesome, because not only does that mean we can get more effective transistors in, but the temperatures will be much lower working with graphene and carbon than they are at the moment. There's people researching with photonic processors that actually work by chucking light around. And in my head, that looks like a big block of crystal just sitting in the middle of a desk with flashes of light kind of sparkling around it. But it's probably nowhere near that gorgeous, and it probably looks a bit rubbish. But the problem with photonic processors is currently they're actually massive, because generating light is something that we haven't reliably figured out how to do at the molecular level. Organic processors, though, so the most powerful computers on the planet are in our heads, and we have no idea how the grey matter, the sludgy stuff that's in our heads, results in consciousness and an ability for me to give this talk and for you to watch this talk and for people to build networking video conferencing solutions that mean I can do this in my office and you can watch it in your office. We don't know how that works, but we're starting to figure it out. And so if we can recreate that organic structure, then potentially we can create processors based on that could be millions of times more powerful than what we've got at the moment. And of course, the other thing that's going on is quantum computing. There are quantum processors, and companies like D-Wave are doubling the number of qubits that they can get into a quantum computer roughly every 18 months. So quantum computing is now kind of hitting Moore's law, but quantum computing doesn't scale linearly. This is fantastic. In a 64-bit quantum computer, each 64-bit register can hold 18 quintillion 446 quadrillion 744 trillion 73 billion 709 million 551,616 different values all at the same time. And then it can choose the one that's right in a fraction of a microsecond. And apparently, according to the book I read about this, the reason it can do this is because there are an infinite number of quantum computers in an infinite number of universes, all running the same program. They each come up with a different answer, and then the one that got it right shares it with all the others. Because quantum mechanics makes no sense, but I love it. Quantum computers will be able to crack 2048-bit RSA keys in sub-millisecond times. Encryption will just go away, but then quantum computers will be able to do new encryption that is uncrackable even if you had a computer the size of the entire universe. Quantum computers at the moment can solve quantum problems, and that doesn't sound very exciting, but an example of one of those quantum problems is plant roots can do things with nitrogen that when we try and do them by creating fertilizer, the carbon footprint on it is enormous, and it's complicated, and it costs a lot of money. If a quantum computer can model how that is actually done by natural processes, and we can recreate that natural process, then the whole process of fertilizing and producing crops and everything can be revolutionized. And that's the sort of thing that quantum computers are going to be able to do. So that's really exciting. A little bit more about that later if there's time. So looking at current trends, computers now, they're smaller, they're faster, they're cheaper, and they are everywhere, literally everywhere. They're in your, this is a list of the things in my house that are connected to the Wi-Fi that I took off the router. There are 8 computers, laptops, desktops, 8 phones and tablets, 2 Xboxes, 1 PlayStation, 2 Nintendo Switches. Yes, my kids are lucky. Dad, can we have... Oh, you've bought it. There's the TV. That's connected to the Wi-Fi. I don't know why. I think it's so it can report to Samsung that I watch too much TV. I've got 3 Sky Q boxes, 2 Amazon Fire TVs. My Samsung Watch and my wife's Apple Watch, they're connected to the Wi-Fi. 6 Echo devices so that I can say, Echo, turn off the lights. And she will. The lights, obviously, some of those are connected to the Wi-Fi. Some of them are connected via the Zigbee thing. 3 books. We've got 3 Kindles in the house. We've got books that are connected to Wi-Fi. I've got a book that where when I go to read a bedtime story to my son, I go, oh no, the book's run out of battery. I'm going to have to plug it in. I'll just make up a story for tonight. The doorbell is connected to the Wi-Fi so that when I'm the other side of the world and somebody rings my doorbell, I can talk to them because of Ring doorbells. The washing machine is connected to the Wi-Fi, so when the washing finishes, a toast notification pops up on the television and says, hey, your washing's done. There's a printer that's connected to the Wi-Fi. There's a camera that's connected. It's just, and actually of those things, these are the ones that you would think of that you wouldn't think of as computers. So, if I take out the Xboxes and the PlayStation, these are the portable devices, the lightweight little things. These are the things that you would think of as just not even, why would those be connected to any kind of computer network? And this is increasing. The Internet of Things is a big deal. And we're just putting tiny little coin-sized computers in places with sensors on them that then just stream readings from those sensors into the cloud so that we can run data science experiments over them. And I think that we as programmers need to start thinking about how to write code for these smaller devices. I think this is going to be a big thing over the next 10 years, partly because of the Internet of Things, but also just because of the carbon footprint of everything that we're doing, all the servers that we're running, all the computers that we're running. The carbon footprint of that is enormous, and if we can shrink that down and run our software on smaller, lower powered computers, then we can help the environment. So you can make a start on that now. You can get a Raspberry Pi 4B. This is an astonishingly powerful piece of hardware, and you can pick the cheap one up for 35 euros. I think the most expensive sort of 4 gig model only costs 50 euros. They've just brought out a version that's built into a keyboard that you can just plug into a television. That's only 70 or 80 euros. And you can get various different takes on this idea. There's the Asus Tinkerboard, which is a little bit more powerful, but not as well supported. For the really, really small things, you can get a Raspberry Pi Zero, and these things go for like £10. And this runs an entire operating system, and you can run .NET Core on it, you can run Java on it, you can run Node.js on it. And you can attach it to a 9-volt battery and run it off a 9-volt battery for 6 months, and it will just sit there and do its thing. There's things like the NVIDIA Jetson Nano. This is for AI. So this is something that we're seeing is artificial intelligence actually happening on the edge devices, on the IoT devices, so that rather than just piping all the data into a massive data center to be processed, they can actually do things like speech recognition, image recognition processing, actually on the device itself. And so you can pick up a Jetson developer kit for around 100 euros. And that's a really fun thing to play with, actually. It's got tensor cores, and it's essentially a GPU that you can run an operating system on. And then there's things like Hummingbird, Orange Pi, Banana Pi, Odroid, which all compete with the Raspberry Pi. And then you have Arduino, and Arduino is a microcontroller, not a microprocessor, and so it doesn't run an operating system. You essentially build an entire application into sort of a unikernel kind of thing, and then you can run that on an Arduino, but that is even lower powered and will run for even longer on a 9-volt battery. And like I say, talking about the energy use, it's projected that by 2030, 20% of global energy will be used by information technology. 20% of the carbon footprint of the world will be computers and servers and devices and things like that. And if we can bring that down, and Apple's M1 chip is a great step on the road to this. They've got an ARM processor that uses 11 watts, I think, peak, where you look at the AMD processor I've got in my computer is 105 watts peak. So moving towards these lower powered things is good for the environment as well. You can already get ARM hosting in the cloud from places like this, Scaleway, Mythic Beast. AWS are doing ARM instances. I suspect we'll see them on Azure and Google Cloud soon as well. And if you can run your service or your website or whatever it might be on an ARM server that's using 1/10 of the power of a regular Intel server, and it runs just as well, then you should do that just for environmental and also for cost purposes. If you want to look into that, I generally give this talk to .NET developers, and I know GOTO is not particularly .NET, but we now have .NET 5.0, which runs on ARM 64 and ARM 32, and there's some great projects on here. These slides I will send to GOTO after the talk so that people can get these links and things. But yes, these are some .NET links for working with ARM, but you can find out how to do it with whatever your preferred platform is. If you've got kids, I've got 2 kids, and one of them's 9, and he's getting into coding, and he still prefers block-based languages. Microsoft have a website called MakeCode, and there's a MakeCode arcade where kids can design simple Flappy Bird style games using a block-based programming language, which you can actually switch to JavaScript if they want to see the real code behind it. And the thing I really like about this is that you can buy these very, very cheap little PCB things with a screen built in, and they can download their game and they can run it on something like this. The BrainPad Arcade is one. It's tens of euros. It's like 40 or 50 euros with a screen and buttons built in, and you can get a case to go on it and so forth. There's the Adafruit Pi Gamer, which is seriously tiny. And then there's the Adafruit Pi Badge, which is even tinier. And then the KittenBot Meowbit. So these are great things to get your kids into coding. And, all kids, they want to make games. They do Roblox, they do Minecraft, they do all these creative games on mobile and on laptops and on Xboxes and things. And you can actually give them something so that they can take it into school and go, hey, look, here's a game I made running on something that looks a bit like a Game Boy. So, and these are all running on these low power devices as well. So that's something that's worth looking at. The next thing I want to talk about is modern primitive technology. So technology that is today roughly where things like that noisy printer were 30 years ago. And the first and most obvious one is our user interface technology. We're at an inflection point in how user interfaces work because of virtual reality. And if you've seen the Ready Player One movie or read the book or listened to the audiobook, basically pretty much everyone just spends all their time in virtual reality because the world sucks and virtual reality is nice, and so that's where they go instead. And inside virtual reality it looks like this, and he's moving around, and it's for some reason when he walks in real life he's walking in the thing but he's not bashing into walls and so forth. And so this is where I think we think we're heading with virtual reality. But at the moment, we have these massive rigs like the HTC Vive and the Oculus Rift, which come with little camera sensors that you have to put up around your room that detect your motion, and you can draw out a space and everything. And of course, many wires to attach the headset to your computer. So you're running around with a 10-foot HDMI and USB combined cable. And of course, you also need a pretty powerful computer to run virtual reality. But this is changing as well now. Facebook just released the Oculus Quest 2, and this is for $300. You get really high-end hardware. This has got a VR-specific CPU from Snapdragon. It's got seriously high resolution, inside-out tracking. So this is entirely self-contained. I have the version 1 of this, and it's completely brilliant. And if you haven't experienced VR, I just want to show you a quick example of a game that I play a lot in virtual reality, which is called Beat Saber.
If you wanna escape with me, come take my hand.
This point, but this is how I exercise. I actually put on sort of gym t-shirt and shorts, and I go and play Beat Saber on. I'm honestly expert. I don't play it on expert. Can't do it on expert. But I play it on this slightly harder setting. And I do this for half an hour, and I have to stop because I'm exhausted. But that's the sort of thing that we can currently do in virtual reality. I think you sort of see people talking about virtual reality desktops and whether traders on stock exchanges could just put on a virtual reality headset and be surrounded by monitors and so forth. At the moment, they're still very heavy. I don't know about everybody else, but I tend to sweat a lot when I'm inside them. And you are closing yourself off from the world around you, which is kind of the issue with virtual reality. But then we also have augmented reality. And this is something that Microsoft kind of spearheaded with the HoloLens. And you can finally buy HoloLens 2 developer kits in the United States. So if you know somebody who lives there, you can get them to buy one and ship it over to you. But this has got sort of a customized version of the Snapdragon 850 CPU. It's got a custom holographic processing unit. And this superimposes virtual objects on the world around you. If you're ever at a conference and you see one of the stands, one of the sponsors has got a HoloLens and letting people play with them, jump on them because it is amazing fun. I was chasing a chili pepper around the Spectrum Center in Oslo a couple of years ago, and it was brilliant fun. Magic Leap, Magic Leap, it was nice knowing them. I'm not sure what's happening with them now, but they had something that actually looked a little more wearable, and they had a brilliant example app, which I'm going to show you now. This guy is just wandering around his hipster apartment with his hipster shirt on. Now he puts his hipster augmented reality glasses on.
Two exciting emerging tech companies announced a new partnership today, which will see the Cheddar Network available on
that nobody else can see. And you can still see all the rest of his apartment around him.
The market's right now.
I think this is going to be a huge inflection point for a lot of things. If you can get the augmented reality headset to a point where it's comfortable and wearable and usable, and you don't look like this guy wandering around his apartment looking like somebody who's just had laser eye surgery. But these are the first generation devices in this space. The HoloLens, we've just got the second generation, which is lighter, but it's still, it's targeted for people who are working. It's not something you're going to wear around the house. But I think back, and I think from 1993 to 2006, in 13 years, we went from the massive brick-like, slow, basically rubbish Apple message pad to the Apple iPhone, which was just, it was, there's nothing in common between those two at all. And so if you take 13 years, how long is it going to take for it to get from something like the Magic Leap to just a pair of glasses that you can put on your face that are just like the glasses I'm wearing right now, but are able to do so much more than the Magic Leap headset or the HoloLens headset could do. Actually, there's a company called Nreal, which is engaged in serious litigation with Magic Leap at the moment, and they've got these, and those are glasses, and this is in 2020, and you can buy this now. You can get a developer kit for this now, and yeah, it's not going to be fantastic, but this is the start. And so I think that this kind of environment where we are going to see the end of screens, we're going to see the end of televisions and monitors, and the whole idea of interacting with information as rectangles, I think, will eventually go. And you'll just have contextual information integrated with your actual environment in ways that mean something to you. The fridge will display, there'll just be an alert floating in front of the fridge going, hey, you're low on milk. We haven't even started to think about how we're going to interact with the world once augmented reality becomes something that happens everywhere. Here's a great kind of concept video of, this is actually from the people who made the Leap Motion, and they have a kit that you can sort of download the parts list for, and you can build the thing yourself. And so they imagine that this is what would replace a phone or a tablet, would be just something that floats in space that attaches itself to the side of your hand. And what is this going to do to user interface design? If we're building business applications in a world that doesn't have screens, are there better ways that you can present data to users so that they can interact with it and so that they can act upon it? And so I think it's worth starting to think about this new approach to user interfaces. I've been learning Unity, which is a game development system that uses C# as its programming language, and it's fantastic, and it's actually really, really easy to get started. But I'm learning it so that I can start to understand 3D graphics and modeling. So I'm working in Unity, I'm working in Blender to create assets to use in Unity to present things on. And Unity compiles to the web browser, and one project I would love to find time to do is to implement something like Grafana or Kibana dashboard, but using the full kind of 3D modeling set of Unity, and then combining that with WebVR so that you could just go into your logs and your alerts and everything and just explore around them. Kind of like in Jurassic Park. It's a Unix system, I know this. But yes, so you can go and get Unity 3D. It's completely free until you are making $200,000 a year from it, and then they ask you for £25 a month. But you can go and grab that, and you can go to the asset store. If you're not an artist, you can just download things to dump in your game. There's a great book, Unity in Action. If you're on YouTube, search for Brackeys. If you like learning from YouTube videos, Brackeys have some great videos on there. If you want to do this for the web, then go and check out aframe.io, and immersiveweb.github.io/webxr is all about virtual reality and mixed reality in the web. And this is kind of an early example of the sort of thing I'm talking about. This is Minecraft Earth right now running on smartphones. But this is where I'm thinking we're going to see the world around us being enhanced. And if you imagine this, but without the phone and just with a pair of lightweight glasses that you can just put on and then go skateboarding around, and Minecraft just appears in the world around you. And maybe the entire world will become like a Twitter timeline, and we'll be able to see the modifications and the sculptures and the art and the messages that have been left around, but just by the people that we choose to follow. Your Facebook friends or your Instagram crushes could just leave things lying around the world for you to find, like creepers and endermen and everything else. So yeah, recommended reading on this one is Snow Crash. If you haven't read Snow Crash by Neil Stephenson, I do recommend it, although it's probably got about half a dozen trigger warnings on it, and it is of its time. So it's not particularly enlightened in terms of feminism and various things that have changed since it was written about 25 years ago. But it does talk a lot about where we might be going with VR. And so now I'm running out of time, so I am just going to blitz through the next few bits because there is more interesting stuff. So manufacturing, this is changing in a big way because we now have 3D printing. And in 1992, this was the first 3D printer, and this cost $100,000. Now you can go onto Amazon and you can buy the sort of descendants of a Darwin RepRap, sort of hand-built 3D printer, and you can pick up ones of these for less than €200. You can get the DaVinci Junior, which is a nice starter one. That's really cheap. You can get the DaVinci Color, which actually is a full-color 3D printer. It uses a special filament, and then it dyes the filament with ink as it's doing the printing. We have the Form 2, which works in a different way and uses resin-based printing, and this costs a lot of money, but you can actually, for around €250, €300, you can now get cheaper resin-based printers. And the thing with resin is you can make much smoother, more high-resolution objects. And that's where we are with 3D printing now. And I think, look, in 89, 2009, 20 years, and we went from that big noisy thing to, there were actually printers that you could put in your bag and carry around and print things out sort of while you were on the move from your laptop. So where are 3D printers going to go over the next 30 years? We're already at the point where people can print things like gadgets. This was at University of California in Berkeley. They printed a working remote control except for the batteries. And this was actually 2003 that they did this. So obviously this has not made it to the mainstream yet, but we are getting to the point where 3D printers can work with metal and plastics and possibly silicon, printing silicon integrated circuits. We're almost at the point of being able to print food. This is an Italian bioengineer printing a meat substitute made from vegetable proteins, which mimics the texture of beef. And it doesn't take much imagination to go from there to the point of Star Trek replicators, where you're actually just, okay, they're condensing things out of pure matter, but potentially being able to manipulate molecules or even atoms and just combine them together. Great fiction book based around this is The Diamond Age, also by Neil Stephenson. Much more enlightened than the last one, and actually my favorite Neil Stephenson book, but set in a world where manufacturing is based on assembling molecules into solids. The reason it's called Diamond Age is because carbon is more widely available than silicon, and so if you can put it together however you like, diamond becomes cheaper than glass, which I think is a fantastic concept. There's a lot of amazing near future concepts in that book. Then we have AI, and AI has just gone completely nuts. And I am just going to blitz through this. We had the Turing test, McCarthy and McKinsey. The Lytle report said it would never only be ever good at amateur chess. expert systems were a waste of time. Deep Blue beat Kasparov. In 2002, we got artificially intelligent hoovers. Boston Dynamics came along. Watson beat people at Jeopardy. Siri appeared in our phone. She appeared in the house. I can't name her. I've got one sitting right beside me. We're going to have driverless cars. We've got the Google Assistant. AlphaGo beat one of the world's best players at chess. Then AlphaZero beat AlphaGo at chess. John Carmack has decided he wants to work on AI. We've got neural processing units in all our phones now so that they can do AI faster. There's AI as a service in all the clouds. There's SDKs for doing it like ML.NET and OpenCV, and there's things you can do to get started learning about ML, but I really would recommend learning about ML. We've got quantum computing, which is coming along really, really quickly, and you can go and play with Q#, which is Microsoft's quantum programming language. You can actually buy time on a real quantum computer from IBM at the Quantum Experience, and great book, fantastic book, Computing with Quantum Cats, explains quantum computing. That's the one that told me that they work by existing in a multiverse in all sorts of places. And we've got nanotech. Nanotech's just completely bonkers. This is some nut stuff going on here with nanotubes and single molecule manipulation and all that kind of thing. If you want to get into that, you need a bachelor's degree, a master's degree, a PhD, and a research position at a really good university. But, have fun. So, in summary then, I think where we are going to end up, in 2029, we're going to get hit by the Apophis asteroid and everyone will die. No, that's not really going to happen. I think by 2029, we will actually have augmented reality becoming mainstream. Apple are going to release their AR headset next year, maybe the year after. Then the year after that, Samsung will release theirs, and then we'll all have them by 2029, and that will be something that we're dealing with. We'll have a huge cultural shift as logistics jobs, manufacturing jobs, farming jobs are all automated, and people get freed up to do hopefully more interesting things. And I think something weird's going to happen there, but that could be fun. But that's in the next 10 years. I honestly think that by 2039 they will have made it to Mars, and they'll be starting to build stuff on Mars. And a lot of that will be driven by 3D printing and the ability to take 3D printers and produce what they need on Mars in situ. And so, manufacturing, you won't get something delivered from Amazon anymore. You'll just download it and go and print it at your neighborhood 3D printer. We'll see a lot more robots, and we're going to start to see human augmentation, bionic limbs. Eventually, we'll get to the point where people who've got bionic arms and legs and eyes and things because of accidents or birth defects, people who've got perfectly functional arms and legs and eyes will just start going, hang on, no, I want those. Those are better. I would like to believe, and I try to believe, that maybe in 30 years' time, we'll have entered that post-scarcity society where people don't have to work and people aren't held hostage and forced to work by the fear of homelessness and everything else. And we can all work together, and people can do the things that inspire them and the things that drive them and the things that they love to do, and share them with other people just for the love of sharing them. And it's a whole hippie thing, and all watched over by machines of loving grace. But I think that is one of the options in our near future, and I would very much love to get to that point. There's a lot of information in this talk, so I made a website. You can go to futurology4.dev, where there are links to more information about lots of the things that were there and the frameworks and so forth. If you want to ask me about any of this stuff after the talk, I'm on Twitter @MarkRendle. Just follow me, give me a ping. My DMs are open if you want to talk to me that way. Also, I have a project that I have to shill, visualreco.com. Go check it out if you're a .NET developer looking to move to .NET 5. That is it. That is the talk. I managed to get through most of it and only ran 5 minutes over. Yay me. Thanks so much. I hope you had a great conference, and I hope that has left you feeling excited to go out there and learn some new stuff. Cheers.